DNS, Domain Name System. 1. Function. Associates domain names with IP addresses, simplifying access to network machines. Without DNS, users must remember IP addresses, which can change and are difficult to memorize. With DNS, users rely on domain names. DNS servers handle IP address changes. 2. Structure. Distributed and hierarchical database. Associates domain names with IP addresses and can store other information. Redundancy and caching ensures high availability and improved performance. 3. DNS tools. NSLookup, available on most Linux and Windows systems for querying DNS via the command line. Example: NSLookup packpub.com returns the IP address 83.166.169.231. 4. DNS operation. Hierarchical system of caching servers, distributed databases on servers worldwide. Process. When a domain is entered in a browser, the computer queries DNS servers to find the associated IP address. If the initial servers lack the information, they query other servers. 5. Configuration. Default. Windows computers use the DNS server provided by the Internet Service Provider, ISP. Alternatives. Other DNS providers like OpenDNS, UltraDNS, or Google DNS can be used for potentially better security and performance. 6. Example of configuration resource. More information on configuring using Google DNS can be found here. https://developers google.com/speed/public-DNS. Key point summary. DHCP requests can be made using client on GNU/Linux or IP protocol configuration/renew on Windows. DNS simplifies network access by mapping domain names to IP addresses. DNS is a distributed, hierarchical database ensuring availability through redundancy and caching. Tools like NSLookup help query DNS information. DNS operations involve querying a series of hierarchical servers to resolve domain names to IP addresses. Windows defaults to using the ISP's DNS server, but allows using alternative DNS providers for enhanced security and performance. Example configuration for Google DNS is available online. Key points. 1. Mechanism overview. The mechanism hides private network addresses from the Internet by making traffic appear to come from a single public IP address. 2. Private address use. Devices use private range addresses, assigned by a DHCP server or router via DHCP dynamic assignment. Private address ranges. 10 0 0 0 0 to 10 255 255 255 172 16 0 0 to 172.31. 255 255 192 168 0 0 to 192 168 255 255. 3. Concept. Networks use private IP addresses internally and connect to the Internet using a single public IP address. This allows large companies and home networks to use fewer public IP addresses. 4. Types of NAT operations. Static NAT. A private IP address always translates to the same public IP address. Allows a host within the network to be visible from the Internet. Dynamic net. The router is assigned multiple public IP addresses. Each private IP address maps to one of the available public IP addresses. Public IP addresses change dynamically, increasing security by making it harder for external hosts to enter the network. Key points. 1. IPv4 technology. IPv4 enables computers to connect to the Internet. Each device gets a unique IP address when connected to the Internet. 2. IPv4 address structure. IPv4 addresses are 32 bits long. IPv4 can manage approximately 4.3 billion IP addresses. 3. Address space limitation. The IPv4 address space is limited to 4.3 billion addresses. IPv4 addresses are composed of 4 groups of 8 bits, allowing 256 different combinations per group. 4. Calculating IPv4 addresses. The total number of IPv4 addresses is 256, 256, 256, 256 is equal to 4,294,967,296 addresses. 5. IPv4 address classes. Class A 100,000,126,255, 255, 255. Class B 128,000,191, 255, 255, 255. Class C 192,000,223, 255, 255, 255. Class D 224,000,239.255, 255, 255 multicast. Class E 240,000,254.255, 255, 255 experimental. 6. Address restrictions. Multicast and experimental addresses cannot be used as source addresses. Additional restrictions include network zeroed, 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 zero, identifier of all IPv4 networks. Network 127, zeroed, zeroed, zero, physical loopbacks. Network 255, zeroed, zeroed, zero, broadcast addresses. 7. Effective address count asterisk. With restrictions, 116,777,216 addresses are removed from the total. 8. Need for IPv6. Due to IPv4 limitations, IPv6 was developed as a replacement. IPv6 addresses are 128 bits long. 9. IPv6 address structure. IPv6 addresses consist of 8 groups of 16 bits, expressed in hexadecimal notation and separated by colons slightly smiling face. Example IPv6 address: FE80, E53F, E43B, add 07:9 cap. 10. IPv6 versus IPv4. IPv6 addresses provide a significantly larger address space compared to IPv4. Key points. 1. PyPI overview. The Python Package Index, PyPI, is the official repository for third-party Python applications. Found at https://pypi.python.org. Aims to be a comprehensive catalog of all open-source Python packages. 2. Using pip to download packages. Pip is the official package installer for Python. Comes pre-installed with Python. Example command: pip install package_name, e.g., pip install requests. Can also be installed using Linux package managers, e.g., sudo apt-get install python pip on Debian/Ubuntu. 3. Alternatives to pip. Conda. Developed and maintained by Anaconda. Comes with over 100 popular Python packages. Download link: https://www.anaconda.com/download. Installation command: conda install package_name, e.g., conda install requests. Independent of the official Python repository but includes networking libraries. Virtualenv. Tool for creating virtual environments in Python. Installation command: pip install virtualenv. Usage example: virtualenv env creates a virtual environment named env. More info: https://virtualenv.pypia.io. PyPenv. Modern tool for managing Python dependencies and virtual environments. Installation command: pip install pypenv. Includes a complete dependency resolver. Guide available at https://realpython.com/pythonv-guide. 4. Network Programming Libraries. Python provides modules for various network protocols. Examples include requests and urlib found in both PyPI and Conda repositories. Key points. 1. Introduction to sockets. The socket module is Python's standard interface for the transport layer. Provides functions for interacting with TCP, UDP, and DNS. Detailed coverage in Chapter 10, Programming with Sockets. 2. Definition of a socket. Defined by the IP address, port, and protocol used. Types and functions for sockets are in the Python socket module. Classified as stream sockets, socket.sock_stream for TCP, connection-oriented, reliable. Datagram sockets, sock_DGREM for UDP. 3. Socket families. Unix sockets, socket.af_Unix for Unix domain sockets. IPv4 network sockets, socket.af_inet. IPv6 network sockets, socket.af_inet6. 4. Creating a socket. Use the socket.socket constructor. Default parameters, af_inet family and sock_stream type. Syntax, socket, socket_family, socket_type, protocol equals 0. 5. Parameters. Socket_family, either af_Unix or af_inet. Socket_type, either sock_stream or sock_DGREM. Protocol, usually defaults to 0. 6. Client socket methods. Connect, host, port. Connects to a remote socket. Example. Python. Import socket. Client_socket equals socket. Socket. af_inet. Socket. sock_stream. Client_socket.connect. www.pactpub.com. 80. 7. Server socket methods. Bind. Defines the port the server listens on. Listen, backlog, makes the socket accept connections and starts listening. Accept, accepts a connection. Example. Python. Import socket. Server socket equals socket. Socket. af_inet. Socket. sock_stream. Server socket bind. Localhost. 80. Server socket.listen. 10.